The world population is expected to reach 10 billion people by 2050. So what is our most valuable asset? I believe it is planet Earth. Hi, my name is Danish Kazmi. I am a researcher in geotechnical engineering at the School of Civil Engineering of the University of Queensland. Sustainable infrastructure is crucial in our paradigm shift towards the circular economy. It is therefore essential to unlock the potential of waste materials to help decarbonize the construction industry and move towards a low-carbon future. This video abstract highlights our joint cross-institutional research introducing a new sustainable approach to improve weak ground for construction. This research was performed collaboratively by the researchers at the University of Queensland in Australia, University College London in the United Kingdom, and others.
Granular columns, also known as sand or stone columns, are traditionally used to improve the bearing capacity of weak soils and to keep their settlement within acceptable limits. Natural or quarried sand or stone are typically used to backfill granular columns due to their higher stiffness and permeability than that of the untreated soil. Technically, a granular column mobilises the passive resistance of in situ soil and acts as stiff elements in the composite ground. The higher permeability of granular columns provides a drainage path that accelerates consolidation in the soil. However, the reserves of natural sand are shrinking, and the price of natural sand has skyrocketed to almost 6 times in the last 25 years. Simultaneously, given the negative environmental impacts of excessive sand mining, we need to develop alternative and sustainable geomaterials that are readily available, cost-effective, and technically feasible.
The ever-increasing volumes of crushed waste glass could be a sustainable replacement for natural and quarried sand in many geotechnical construction applications. This could provide both waste recycling and sand conservation benefits, combined with other locked-on benefits such as reduced pressure on landfill, biodiversity conservation, and developing a circular supply chain of waste glass. Interestingly, our previous research favorably shows that crushed waste glass has geotechnical behavior similar or sometimes even superior to that of traditional construction sand at optimal particle size and gradation. Additionally, previous research shows that several parameters could influence the geotechnical performance of granular column reinforced soils. Those parameters include relative density, particle size and angularity, gradation and durability parameters of column backfill, together with the area replacement ratio, the types of granular column, the stress concentration factor, and others. However, the role of particle size of column backfill yet remain largely under-researched.
This study investigated how the particle size of a granular column backfill affects the geotechnical behavior of reinforced soil and compared with that of unreinforced soil. Kaolin and crushed waste glass were used to represent weak soil and granular column backfill respectively. The crushed waste glass with different particle size ranges from fine to medium and coarse was separately used to install a granular column in kaolin using the replacement method. The column kaolin geocomposites were carefully prepared to correspond to practical field conditions. The shear strength and consolidation behavior of the prepared geocomposites were investigated. Cubical geocomposites with lengths, width and depth equal to 150 mm were prepared for shear strength testing. In contrast, cylindrical geocomposites with height and diameter equal to 150 mm were prepared for consolidation testing. The geocomposites for the consolidation test were prepared to almost the same state as those in the direct shear test to help ensure consistent test conditions and to facilitate comparison. The end-bearing crushed waste glass columns were installed in kaolin at an area replacement ratio of 16%. The relative density of the crushed waste glass column was 60%. The prepared geocomposites were subjected to single-stage, stress-controlled direct shear testing and sheared at a slow rate of 0.02 mm per minute under different normal stresses, and the shear stresses and deformations were automatically recorded. Likewise, The geocomposite were subjected to different normal stresses in the consolidation test, and the settlement and other measurements were automatically recorded. The benefit of using a large direct shear machine and a large consolidometer is that they help minimize the scale effect and to model the field conditions more accurately.
The test results showed that the shear strength and consolidation behavior of kaolin reinforced with a crushed waste class column was sensitive to the particle size of crushed waste class used. Installing a crushed waste class column of any given particle size range in kaolin increased the peak shear strength of the geocomposite compared to that of the kaolin-only specimen. The geocomposites containing a crushed waste class column of medium particle size showed the highest increase in friction angle, increasing from 14 degree for kaolin-only specimen to 20.7 degree for the geocomposites, potentially due to the higher placement density of the medium crushed waste class particles, leading to a superior particle interlock. The geocomposites containing a crushed waste class column of fine particle size showed the lowest friction angle and a relatively lower shear strength under higher normal stresses compared to the other geocomposites tested. The potential reason for this finding could be the higher void ratio of the fine crushed waste class particles corresponding to a given relative density, in addition to penetration of surrounding kaolin into column, creating a weaker smear zone that reduced the overall stability of the column. The consolidation behavior of geocomposites containing any given particle size of crushed waste class column was superior to that of kaolin-only specimen. As expected, the kaolin-only specimen typically showed the highest settlement and took the longest time to settle compared to all the geocomposites tested. Installing a crushed waste class column of any given particle size in kaolin significantly increased the average hydraulic conductivity of the geocomposite due to the higher drainage ability of the crushed waste class column. In particular, the geocomposite containing the coarse crushed waste class column showed the highest average hydraulic conductivity, followed by that containing the medium crushed waste class, followed by the fine crushed waste class. Also, the average compression index, coefficient of secondary compression, and coefficient of volume compressibility of the geocomposite containing a crushed waste class column of any given particle size were found to decrease compared to that of the kaolin-only specimen. Overall, the findings of this study showed that at optimal parameters, crushed waste class could potentially serve as an alternative and sustainable geomaterial to backfill granular columns for ground improvement. This study is among the first ever to study the effect of the particle size of a crushed waste class column on the shear strength and consolidation behavior of a reinforced kaolin. It is expected that this study will serve as a platform for future research on this topic. As a direction of future research, we suggest investigating the effect of particle gradation and angularity of the crushed waste class column on the behavior of a geocomposite. It would be helpful to investigate the effects of groups of crushed waste class columns, together with studying the effect of geosynthetic encasement around crushed waste class columns. Importantly, we suggest performing large-scale model and field performance tests to confirm the results of laboratory-scale tests. Thank you for watching this video. For more information, please read our research article